Okay, this is Gas Laws, Part 2 Notes. The bell work was comparing three different soda cans. You have Coke that's on ice, one that's regular, and then one that's in boiling water. And so it asks which soda has the can with the highest kinetic energy, and it would be the one that is boiling. So this one would have the highest kinetic energy, and the pressure inside the can increases because the particles begin to speed up. The first gas law that we learn is Boyle's law. For a given mass of a gas at a constant temperature, the volume of the gas varies inversely with pressure. So, Boyle's law is P1V1 equals P2V2, or you can rearrange it like this, but what I did in class was gave everybody this puffy cloud of greatness, because this is our first major equation. A good way to remember it is that we boil peas and vegetables. Also important to know is that when you increase, if you increase the pressure, the volume will decrease. We call that an inversely or an indirect relationship. A gas is collected in a 242 milliliter container. The pressure of the gas in the container is measured and determined to be 87.6 kPa. What is the volume of this gas at 101.3 kPa? Assume the temperature is constant. So a big part of these problems is going to be reading and annotating the problems. In order to really understand the problem, you have to pick it apart and write out the variables and the numbers that are given. So to start out, there's a pressure of 87.6 kPa, and that's right here. Second, you have a second pressure that it moves to at 101.3 kPa. kPa, from notes number 1, are units of pressure. The first volume that's given is 242 milliliters, and we don't know the second volume. So I'm going to put a question mark here. We're using Boyle's law, P and V. We boil peas and vegetables. And so it's just a matter of taking these numbers and plugging them into this equation. So here, the numbers plugged into the equation. You have your pressure 1, your V1, your volume 1, excuse me, pressure 2, and then we're looking for V2. So after plugging in and solving, you get 209 milliliters. The second law is called Charles' law for temperature-volume changes. The volume of a fixed gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So in Boyle's law, we held temperature constant. That's why we only used P and V. Here in Charles' law, we're keeping the pressure constant, so we're only going to use volume and temperature. So in class, I gave everybody another puffy cloud of greatness here, because this is an equation that you will need to know for the test. So in this case, when the volume increases, if we increase the volume, we are also going to have to increase the temperature. And so we call this a direct relationship. A good way to remember this is Charlie Brown's Christmas is on TV. So Charlie for Charles Brown, Charlie for Charles' law, and TV for temperature and volume. This picture illustrates the direct relationship. So again, this is directly related. And so basically, temperature's here, and volume is up here. So when one increases, if we increase the temperature, we're also going to have to increase the volume. And vice versa. If we increase the volume, we're going to have to increase the temperature. That's exactly what this picture below shows. We have a certain volume here, and what we do is we increase the volume, and you'll see that the gas molecules in here are moving a lot faster because they have picked up thermal energy. A sample of gas at 15 degrees Celsius and 1 atm has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atm? So let's pick apart the problem. We have a gas at 15 degrees Celsius and 1 atm. So 1 atm is a pressure, 15 degrees Celsius is a temperature, and then we have a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atm? So this 2.5 is a volume, and this 38 degrees Celsius is a temperature, 1 atm is a pressure. You'll notice here that this pressure stays constant the whole time. And when that happens, if we keep pressure constant, we know that is Charles' law. Okay? So we're going to be using the law that we just looked at, and here it is, right here, this is Charles' law. Okay? So, number one, we have a temperature, but it needs to be put into Kelvin. Kelvin. So, that's why we add 273. Okay? And that's going to be, you're going to have to do that each time that you have a temperature in Celsius. We want to get it into Kelvin, units of Kelvin. Next, we have another temperature, 38 degrees Celsius, same thing. We need to add 273 in order to get it into a Kelvin temperature. Next, we're given a volume of 2.58 liters, and we want to know what the volume is when we change that temperature. So, we're plugging in. This equation is down here. We're just plugging in the numbers in the right spot. After we do that, we will get an answer of 2.79 liters. So we increase the temperature from 15 degrees Celsius to 38 degrees Celsius. What happened to the volume? Well, it went from 2.58 to 2.79. So as temperature increases, guess what? Volume increases. That's our direct relationship. Third law we talked about was Gay-Lussac's law for temperature-pressure changes. The pressure of a gas is directly proportional to the Kelvin temperature if the volume is kept constant. So, third law, we're keeping one different variable constant this time. In this case, it is volume. We're keeping volume constant. Another puffy cloud of greatness for our third equation here. This is Gay-Lussac's law. P1 over T1 equals P2 over T2. Okay, here's a variation of the equation for solving purposes, but this is the general form that you need to know. We remember it like this. We say that Gale drives a PT Cruiser. So if that helps you remember it, go for it. If not, find your own way to remember it. This picture illustrates Gay-Lussac's law. We have an ice bath on the left side and then boiling water on the right. And so you'll see that the kinetic energy of the particles is less on the left side as it is in the right side. So if we increase our temperature from cold to hot, let's see what happens to our pressure. We have 1 atm here, and it goes to 1.37 atm. So if we increase the temperature, then we will also increase the pressure. A 2-liter flask contains helium gas at a pressure of 685 torr and a temperature of 0 degrees Celsius. What would be the pressure in the flask if the temperature was increased to 150 degrees Celsius? So what we've done is increased the temperature in the flask, and we are keeping the volume constant. Okay, so I'm going to pick apart my problem. So we have a pressure of 685 torrs, temperature of 0 degrees Celsius. So that would be P1 and T1. Those are our initial conditions. What would be the pressure? So we are looking for P2 if the flask increases to 150 degrees Celsius. So T2 is 150. So I'm going to write out everything that I'm given. P1 is 685 torrs. Pressure 2, we don't know. We're trying to figure it out. Temperature 1, make sure that you put temperatures into Kelvin by adding 273. That's important. Okay, the second temperature, Same thing, you got to put it into Kelvin. Make sure you add that 273. Okay, over here is our Lusak's law. P1 over T1 equals P2 over T2. So we're just plugging in the numbers. 685 torr over 273 Kelvin equals P2 over 423 Kelvin. So after you solve for P2, you get 1060 torr. So let's see what happened. We went from 685 torr to 1060 torr. So pressure increased. Let's see what happened to the temperature. Well, we know that the temperature went from 0 to 150, so the temperature also increased. That is our direct relationship. If you put all three of those laws, Boyle's, Charles, and Gay-Lussac's law, together, you get something known as the combined gas law. And a good way to remember that is peas and vegetables on the table. So peas for pressure, vegetables for volume, and then they're on the table, temperature. So peas and vegetables are on the table. P1V1 over T1 equals P2V2 over T2. If you cancel out terms remaining constant, we can derive Boyle's, Charles, and Gay-Lussac. So what do I mean by that? Well, you have this law. If you memorize this, you've already memorized the first three gas laws. Okay, because if you hold one constant, the others will represent those laws. So let's look at that. So here's the combined gas law. In Boyle's law, we held temperature constant. So if we cross out temperature on both sides, we keep it constant. There you go. There's Boyle's law. Peas and vegetables. We boil peas and vegetables. There you go. What if we decide to hold another one constant? Let's say that we hold pressure constant. Okay? Let's hold pressure constant. We get V1 over T1 equals V2 over T2. Well, there you go. That's Charles' law. And then finally, what if we decide to hold volume constant? If we hold volume constant, those can cancel. We get P1 over T1 equals P2 over T2, and that is Gay-Lussac's law. So if you remember this combined gas law, you are able to derive the other three gas laws. Here's an example of a combined gas law problem. A helium balloon is filled, and it has a volume of 3.4 liters at 25 degrees Celsius and 120 kPa. So what is its volume at STP? So let's pick apart the problem. We have a volume of 3.4 liters, temperature of 25 degrees Celsius, and 120 degrees kPa. What is its volume at STP? So they give us the initial conditions. They say that we have a volume, we have a temperature, and we have a pressure. We want to know what the volume is at STP. Well, STP from our notes in the previous video is 0 degrees Celsius and 1 atm. Okay, so that's important to know. Make sure that you understand that STP is 0 degrees Celsius and 1 atm. So here's our volumes. We're given 3.4 liters. We don't know the second volume. Our pressure to begin with is 120 kPa. Our second and final pressure is at STP, which was 1 atm. But what we have to do is convert it from atms into kPa so that our pressure units match. That's important. Then our first temperature, make sure that you are adding 273 Kelvin. Second temperature, 0 degrees Celsius. Make sure that you add the 273 to get into Kelvin. So here's the combined gas law. And it's just a matter of plugging in your numbers. Okay, after you do that, you will get a total of 3.69 liters. And finally, the last example, another combined gas law problem. A flask contains 1.4 liters of an ideal gas at 50 degrees Celsius and a pressure of 1.44 atms. If the gas is compressed down to a volume of 0.7 liters and the temperature is raised to 100 degrees Celsius, what will be the new pressure in the container? So initially we have a volume of 1.4 liters, a temperature of 50 degrees Celsius, pressure of 1.44 atms. And then we change our conditions to a new volume, a new temperature, and we are looking for pressure. So let's go through it. Here's our volume. We start with 1.4 liters, we half it to 0.7 liters. The pressure, 1.44 atms, and we are going to be looking for a new pressure. And then our temperatures, we take and we double it from 50 to 100 degrees Celsius, but make sure that you add 273 to get into Kelvin. Here's the combined gas law. All you got to do is plug in the numbers from the problem, and after you solve, you get 3 atms.